Now, what we'll do that after the formal introduction of Professor Rai Choudhury by Professor Mutri Bhattacharya, we will start our lecture session. And during the session, I request all the participants to keep their microphone in mute mode. Otherwise, noise used to come and it essentially disturbs the presenter. And nobody will use the presentation mode. Only the speaker, Professor Rai Choudhury, will use the presentation mode. So I request all the participants not to use that presentation mode and keep your microphone on mute mode. And what you will see that once Professor Rai Choudhury starts presenting, you will see two icons against his name. Out of that, against one icon, you will see that Shomok Rai Choudhury presenting. So you have to pin that icon on your mobile or laptop or electronic devices to get the presentation on your screen. So essentially, these are the two rules we are, and the rest of the things you are already matured enough and you have got experience through several seminars organized by JBNSTS on virtual platform. So I hope all of you will cooperate. And with this introduction, I will request Professor Mutri Bhattacharya to introduce Professor Shomok Rai Choudhury. We are already 185 participants on board. Right. Thank you.
Okay. So it's my privilege to welcome Professor Shomok Rai Choudhury at the digital platform of JBNSTS. At first, I like to ask our scholars, I like to inform our scholars that Professor Shomok Rai Choudhury is also a senior scholar of Jagadish Basu National Science Talent Search. So it will enhance your enthusiasm to listen to him, because once upon a time he was also a scholar. Professor Rai Choudhury is a versatile scientist. He's a renowned scientist, and several times I have listened to his lecture, and every time it is mesmerizing. So astrophysics today, I think it's really a privilege to you that you will be listening to his lecture on black holes. So Professor Rai Choudhury started his career with Presidency College in BSc Physics Honors from Presidency College, and in West Bengal he won National Talent Search Scholarship National Talent Search Scholarship, then JBNSTS Scholarship, and after that he moved to Trinity College, where he did his in Trinity College he did his graduation with physics, and then he went to the after Trinity College he went for PhD to the University of Cambridge, where his PhD thesis was Gravity, Galaxies, and the Great Attractor Survey. So you understand what exciting the name was. And after that, he went to University of Cambridge. There, and he owned the Harvard. He went to Harvard Smithsonian Center for Astrophysics. Then he was a tutor there also in Harvard University. After that, he was the faculty in School of Physics and Astronomy in University of Birmingham. Then he came to India. He was a professor at Presidency College. He was also the dean there. And now he is the director of Inter-University Center for Astronomy and Astrophysics. And also he is a visiting researcher at the Astrophysics and Space Research Group, University of Birmingham. So you understand how wonderful is his total journey. And I think this journey will encourage you. It will be a great encouragement, inspiration for you to listen to his lecture today. And after the lecture, definitely he will be discussing with you your different queries. And I welcome Professor Rai Choudhury, that in spite of his busy schedule for academics and administration, because he is leading a large research group, he has published in several journals, won several awards. He even won the gold medal in Presidency College. He won the Isaac Newton Studentship in University of Cambridge, INLAC Scholarship for University of Oxford. And with this formidable biodata, it's really a very happy afternoon that we'll be listening to his lecture. Professor Rajudhuri, please.
Can I add something?
Yes,
Thank you.
sure.
Paramita.
Professor Rajudhuri is like he can be considered as the Dada of JBNSTS scholars. He's a very, very informal person in that sense that he has helped us in nurturing many students who are interested in astrophysics. Even when he was a postdoc student at IUCAA, he helped many students from JBNSTS to go and work there as research projects. And he's always had this special place in the corner of his heart for JB scholars. So I wanted to say this to the JBNSTS scholars: take full advantage of this situation.
Thank you.
Thank you, Shomak. Yes, over to you now.
Thanks so much, Didi. Let me just share the screen and then I'm going to start. Just a moment.
Sure.
Let me just figure out whether I can do, because sometimes Google has a problem. Now, has it come? No.
Not yet.
Can you see whether you have enabled me to actually do that?
Yes. It is enabled. It is open for all. That's why I said that no other person should use it. It's you just need to go to the right.
It is asking me to share and an entire screen, but not a window.
It's also possible.
Quickly check whether that is a problem.
No, that's not a problem. What you do, that you do one thing. You just open your slide first on your computer.
Yes.
You just open the slide and then make it maximize. And now you open this Google Meet window. After that, you go to the present now mode and you will see two options, that share screen, entire screen, and share window. Now you have to select the share window.
Yes. So I'm doing a select window or screen.
Right.
But it's letting me share the entire screen. But let me try that either. Can't share your screen. Okay. So sorry about this. This is a problem. I mean, I've used Google Meet with share screen before. Yeah. But this hasn't.
No, but Abhijit, Shomak is right. When I'm trying to share something from my end, it's only allowing me the full screen option. It is not allowing me to open a window.
Is it possible to transfer, say, make me the co-host or something like that, which sometimes works? Certainly works in the
There is
Zoom.
no such option of transferring here.
Yes, there is.
Let me try. Let me try if I can a different browser, because I'm using Firefox. Maybe Google Chrome.
That might be.
This is I've done this before. I mean, it's not that I'm using. This is my fourth video conference today.
I'm checking from my end. There are another options.
Let me see. I'll try
Chrome.
If we can transfer the ownership to Shomak.
Just a minute.
Because I've been doing that with Shanchari for all the meetings that I've held.
I'm checking for that.
If you check out, if you first just hear me out, if you check, Abhijit, if you move out, if you log off, and then you open your Google Calendar and click on the today's meeting, then on your top right-hand corner, there is a drop box which says change owner. So the moment you click change owner, you can type Shomak's.
Actually, it's a problem of the server, because the thing what it's already been said. Many people have already
Started
presented the screen.
yes,
Yeah.
yes, yes.
So it's a problem of the server he is using right now. Let him try with the other search window. Let us wait. He has just opt out, and now he will log in again. Sometimes what happens, those iPhone or these other Firefox servers, they restrict.
Now let me see if it works.
Yeah.
So I'm back and in a different browser, and I am going to. Okay, it says I don't have permission to use the screen. So somehow. But Obviously, you use this all the time, right? I mean, this
Yes,
you
yes.
use the same.
You have seen that many people have already came into the presentation mode. They have started presenting and all this.
Let me try. Let me try this. I've now.
Sir, may I tell you something?
Yeah. Yes.
Yes.
Sir, this is Momita. Sir, once you just leave from this page only. Okay, just exit from this page and then enter.
I needed to.
At that
I needed.
one. Yes.
Yes.
So
Now
that-
it's coming.
Yes, sir. Now it's coming.
So what I did was I had to turn on the sharing option somewhere else. So it's good to know. So can you see the now?
Yeah. We can see it. You just go to the full screen mode, then you will see the presentation at your end, and we will see the presentation as well as your picture. Yeah.
So right now, so that's excellent, and thank you very much. Let me go and see whether I can actually see other people. Is it happening? Is it still there?
Yes, it's happening. Yeah. Perfect.
Right. Thank you very much, and sorry about this glitch. But thank you very much, and thank you very much, both Moichidi and Paramita, for this resounding kind of introduction. It's embarrassing after anticlimax after that. So I'm very proud to be a JBNSTS scholar, and the journey that Moichidi talked about, it wouldn't have happened if I hadn't been a JBNSTS scholar. I think I owe JBNSTS the fact that it kind of started me on a scientific career, got me interested in science. I don't know whether it happens nowadays, but in those days we could go all around India looking at various research institutes all over India. In those days, research institutes and universities where they had research did not interact with other colleges and students. And so through JBNSTS, this was possible. Nowadays, you can do summer studentships in various places. I was the first summer student at Raman Institute, Bangalore, ever. And that was because the year before, JBNSTS has introduced me to Raman Institute, Bangalore. So, these kinds of things are very important in a young student's career. And I'm so glad that so many of you are here, so that not only I'm talking to you, but I can also share with you aspects of my work. And I hope so. What I've done here is, I know that a lot of you would be physicists, a lot of you are engineers, or have technical applied knowledge of physics, but a lot of you are also not physicists. And so I've kept the talk very general. So I think many of you might get a little bored if you know a lot of what I'm going to talk about. So bear with me, but I want to talk about some very interesting and important contemporary issues. And what I'm also going to do is, of course, have a discussion with you after I talk about this. I also know that Soumitra in this series talked about black holes from a theoretical perspective. And so I thought I'd concentrate mostly, but I'll have to introduce black holes, and you know a lot of them. But I talk about how black holes are observed. And this is actually a very new subject because back in the time Moitridi said I did my PhD in Cambridge. Of course, one of the first lecture course on black holes I took was by Stephen Hawking. And Hawking in those days, and I'm talking of the late 80s, was absolutely sure that black holes can never be observed. In fact, his famous bet with Kip Thorne, who got the Nobel Prize recently, where he had said that you cannot, how can you observe black holes? And so I'm going to talk about how we are so sure that we are not only observing black holes, but actually having great fun doing it in many different ways. So I'll start with Newton and his theory, which we learn about in school, which says gravity essentially is a force, right? That's what we learn in school. All objects have gravity, and you know all this. So essentially everybody here knows that the picture that Newton painted for us describing gravity, and that is every single object which has mass has a force of gravitation with which he pulls everything else. And what comes from that is the notion that that for every gravitating object, there is a velocity above which, if you can go, then you can escape from the object. What does that mean? That means that you can escape from the gravitational potential of that object and go away without returning to that object. So like you throw up a stone, it comes back, you jump, you come back to the earth, but above a certain velocity, you can escape and still have the gravity pull you, but you have enough kinetic energy that you cannot come back. And so this is something that we learn in school. Newtonian gravity gives this expression that the escape velocity is this very simple expression. This simple expression, can you see my cursor on the screen? Is the cursor visible?
Yes, sir.
Yes, good. So sorry, I got out of thinking. Yeah. So this just means that this escape velocity is proportional to mass divided by radius, right? And there's a square root. So mass is in direct proportional to this escape velocity, but in the denominator we have radius. So this just means that we can, from classical gravity, actually black holes are a consequence mostly of the Einsteinian way of looking at gravity. But classical gravity predicts black holes too, and that's what I wanted to impress upon you. That Newton's laws gives this idea that if you have an escape velocity, and then you make this assumption that nothing can go faster than the speed of light, which is not there in Newton, but then that means that it leads you to this idea that if, for example, the escape velocity from any object is the speed of light or more than the speed of light, then nothing can escape from this object. And so that leads you to a definition or a conception of black holes. It's mathematically, it doesn't give you the exact expression because you can't use this expression very close to the speed of light, and Newtonian gravity is incomplete in that regime. But at least conceptually, it tells you what a black hole would be. That's it. So how can you make the escape velocity as high as the speed of light? You can make it in two different ways. The escape velocity is proportional to m over r. And so you can make it such that you can make it by increasing mass, which means the more mass you put in an object, the more its escape velocity is, to make it sufficiently massive that its escape velocity will be greater than c. But in reality, in the universe, how do you make such an object? The other interesting way of doing it is that you can decrease radius. Radius is in the denominator. So So you can take any object, including you, and if you increase the radius, then eventually this escape velocity, this quantity is going to increase above C. So that means that we can turn any object, in principle, in terms of physics, we can turn any object into a black hole. So the idea of black hole is then that this escape velocity has to be exceeded, has to exceed the speed of light. Now, if you look at what these numbers are, for the Earth, the escape velocity is 11 kilometers per second. That goes to 43,000 kilometers per hour. So there is no way you can drive a car fast enough to escape from the Earth, right? And this escape velocity is pretty formidable. And one of the reasons you can't really escape from the sun is that the escape velocity from the surface of the sun is already quite high. But if you then turn that into a radius, which will define the size of the object, if you take that object and make it into a black hole, we call this the Schwarzschild radius, and that is given by this expression. And so you can take any object and make it smaller than that object, that radius, then it turns into a black hole by that expression, which means that the escape velocity becomes more or equal to the speed of light. So for the Earth, that radius is less than a centimeter. And that is why you see it's very hard to make the Earth into a black hole. In principle, it is possible, but you can't make it into a black hole. And you read all these news items about CERN conducting experiments where once they turn it on, this high energy experiment will turn the Earth into a black hole. And you can see how completely rubbish such a statement is. Because the only way you can do that is to compress the whole of the Earth into a sphere which is smaller than a centimeter. For the sun, that particular radius is about 3 kilometers. Well, that's possible, and that's actually how black holes are formed in the universe. Actually, for the sun, for our sun, this is not going to happen. Our sun is not going to turn into a black hole, but in principle, it is possible. Right. So the idea of gravity then evolved into in the 20th century into something else, because Einstein came along, and Einstein realized that there are all these limitations to gravity, particularly when you look at velocities close to the speed of light, and also energies that are very high, masses that are very high. Newton's gravity is incomplete. And in particular, in the way it looks at the fact that gravity is a force, which means that it's essentially an invisible string. It attracts two things. That description is actually wrong, and that is because, for example, Einstein thought out of the box. He thought, if you look at Einstein's life, he was thinking about such things from when he was a child. He wrote essays at the age of 14 about what would, for example, gravity do if, for example, somebody's traveling at the speed of light with a mirror. Would you be able to see your own image in the mirror? Things like that he was worrying about. And he also realized that if things are moving very fast, then this concept of gravity being a force between two objects cannot describe it, because by the time, for example, two things which are pulling each other by gravity has moved very fast. By the time because no information can travel faster than the speed of light, if something's moved very fast, how does it know where the other object is and which direction it's being pulled, right? Because there is a finite lag between the information coming from an object to reaching an object, right? So Einstein realized that gravity has to be local. And if you've attended Soumitra talk, he must have talked about this, and the idea is that Einstein reformulated things and said, look, actually gravity is nothing, is not a force. It's actually an effect due to the curvature of space-time. It's a local effect, and you can explain everything that Newton proposed by this effect, the fact that mass distorts space-time, and then the gravity manifests itself as an effect of of the distorted space-time. Right? So everything moves along space-time, along along trajectories which take the minimum amount of time or a minimum amount of something, and then it takes minimal paths along space-time. And so so light, for example, would travel along space-time, and space-time is curved. Light rays would bend. In Newton's theory, for example, light doesn't have mass, so gravity wouldn't have any effect on light. But in Einstein's theory, it actually tells you that light would certainly follow space-time, and so it's consistent with what you see. Actually, you see the bending of light. Right. So the idea in Einstein's idea is that here's the sun, and it bends space-time locally, and the Earth is caught in this bent space-time, and all it does is it can't escape from the sun because it's caught in this kind of well of gravity, and it's moving in there because it has angular momentum, and it's trapped in this curved space-time. So that's a wonderful concept, but it leads to some very interesting predictions, and so those predictions throughout the last 100 years, we have seen how those predictions have one after another been confirmed, leading us to believe in the Einstein picture, right? So Einstein gave us a way of dealing with then this picture of black holes, and of course black holes would be a case where this particular distortion is very, very deep. It is so deep that nothing can come out. So here, for example, if the Earth has quite a lot of kinetic energy, escape velocity, it can get out of this dip in space-time and go away. So that is the Einsteinian way of looking at escape velocity. But the black hole is such that the well is so deep, it's actually infinitely deep, quote unquote, such that even light cannot come out of that well and escape. And so that is why it is a black hole. So that is the general picture, and it makes sense in this particular scenario. So Einstein gave us this idea of how to actually describe the effect of gravity, and that helped us quantify black holes, right? So, but within a year of Einstein's publishing his general theory of relativity, which is his description of gravity, Carl Schwarzschild, who was a German mathematician, took his paper, and he was actually fighting in the First World War. He was on the Russian front as a German soldier, and he had a little notebook with him, and he was trying to solve Einstein's equations, and he actually solved Einstein's equations in a spherically symmetric environment, and came to the conclusion that he could find a metric that describes what the space-time would do around a black hole and around very dense objects. And so this is why we call that the Schwarzschild metric. And we already heard that the size of the black hole comes from that, the radius of the black hole, the Schwarzschild black hole. Carl Schwarzschild did this within 9 months of publishing the Einstein's theory being published, but he was dead before his theory was published. He was killed in the war. But before that, he sent a little postcard back to Einstein, saying that this is how he'd done it. Einstein published it on his behalf. And we now remember Schwarzschild's work, which was done in the trenches in the First World War in Russia, on how to deal with the space-time around dense objects. But that's just a way of describing space-time, and that gives a formalism of looking at black holes. The person who told us about how to actually make a black hole happen in a real context was Chandrasekhar. So Chandrasekhar, you all know the story. I mean, he was, of course, he thought about all this quite a bit. As an undergraduate, he used to visit C.V. Raman in Kolkata at the Cultivation of Science in Bhowbajar, and in his library, in the library of IACS, he found volumes of Astrophysical Journal, which he started to read and got interested in this topic. And his uncle, of course, was pushing quite hard to keep up with such things. And he visited twice, in fact, 2 summer vacations during his undergraduate days in Presidency College Madras. And he decided that's what he wanted to do. He also was looking at quantum mechanics, and quantum mechanics was being invented at that time. And he realized that if he could apply quantum mechanics to this problem, he could actually find a nice description of what happens to stars after they finish their life. And so he set off to Cambridge, and by the time he'd reached there, when he got there, he actually worked with Fowler and Dirac, who were his supervisors. But he'd essentially sorted out a lot of this issue even while he was preparing to do his PhD. So this is essentially the picture of the black hole, right? So we know that, I'm not going to go into the astrophysics, the standard astrophysics, but what happens when stars die, according to Chandrasekhar, is but what do you mean by die? Stars are not living objects, but the idea is that stars are objects where there's an equilibrium between the gravity of a ball of gas and the fact that it produces radiation at its core from nuclear fusion. And so because nuclear fusion involves fusing together hydrogen or helium nuclei in producing this energy, that fuel will finish at some point. And once that finishes, the star runs out of fuel, and so it quote unquote dies, which means that it cannot produce any more energy from nuclear fusion. And at that point, many things can happen to it. It can, for example, just collapse very meekly into something called a white dwarf. It can, for example, have a case in which the whole thing can explode, or it can collapse. Part of it can collapse, and part of it can explode in a supernova explosion. All this stuff is standard astrophysics now, and the part that collapses, the part that implodes, can turn into a white dwarf or a neutron star or a black hole. And Chandrasekhar laid out, using basic quantum mechanics, laid out some prescriptions for what happens depending on the mass of the star and its rotational properties, what happens to a particular star. We now know, for example, our sun is too small a star for it to explode and turn into a black hole. It will turn into a white dwarf when it finishes in 4.5 billion years or so. It's fuel, but stars that are maybe 4 or 5 times the mass of the sun will turn into a black hole. And things that are, for example, if it loses a lot of mass, a star, and what it's left behind is 1.5 times, 2 times the mass of the sun, it can turn into a neutron star. So these are standard astrophysics. But the idea is that astrophysically you can make black holes this way. Now, this is why I just wanted to show you. This is why we can't see a black hole, right? Because this is a picture of a black hole. A black hole is black. It emits no radiation, and this is why somebody like Stephen Hawking and various other very famous astrophysicists would have prepared to bet that there is no way one can actually detect black holes. Nothing comes out of it. All our information from the universe is based on radiation that comes from black holes, or from celestial objects. So we see stars. We can't go and touch our objects. We can't go to them. We see them through radiation, and so there is no radiation that can come out of a black hole. But the idea is that black holes are extremely extreme objects. They're extreme objects, and so the idea is that if a black hole is there, then there would be some extreme physical phenomena happening around them. And the idea is then to look for such phenomena rather than try to actually detect the black hole, which you can't. Now you can, but you're looking at the surroundings of black holes, and black holes are so extreme that they are very difficult to hide. Okay, so we know now there are at least 2 different kinds of black holes. We just talked about the stellar mass black holes that come out of stars evolving. So these are end products of the deaths of stars, right? And so they have to be smaller in mass than stars. And we know that in our galaxy, for example, the most massive stars are something like 100 times the mass of the sun. And so we expect black holes to be much smaller than those ones. But we also know that in every single galaxy, right in the middle, there is one black hole, which is a very, very massive. And they can range from 1 million times the mass of the sun to a few billion times the mass of the sun, 10 to the 6 to 10 to the 9. Now, those things can't come from single stars because there are no stars that are massive, as more massive than those. So we don't know how those come in, but we know that we've now detected over the last 30, 40 years, I've myself detected many of them, which are cores of these galaxies, and they're very, very supermassive. And now, of course, there is a big discussion as to why there is this gap. Why is 10 to the 2 and 10 to the 6? Why aren't there any black holes that are, say, 10 to the power 4 times the mass of the sun, 10 to the power 3? And this is a controversial topic. A lot of people think that we have discovered such things. A lot of people then point out and say, look, no, what you've discovered is not what you think. And so there is a big debate going on right now. So let's see how, I'll talk about 2 or 3 methods today, if time permits, in the next 15, 20 minutes, about how we find these black holes. So one direct way of doing it is to look at a black hole, and as I said, you can't hide a black hole. Even if you can't see it, there will be stars around them, and they will move very fast, right? So here we live in a galaxy called the Milky Way, and if you look at the galaxy's sideways view, we are a planet around the sun, which is about 8,000 parsecs or 25,000 light years from the center of the galaxy. The galaxy is very, very thin, and this is a face-on view of the galaxy, right? And you can see, and in the middle, right in the middle here, there is a supermassive black hole. All galaxies have it. All big galaxies have it. So this is what the galaxy looks like from the side, as you can see. There's a lot of dust in the plane of the galaxy, but if you're looking towards the plane of the galaxy this way, you will see that there's a big band of stars in the sky, and that's called the Milky Way, or Akashganga in Indian languages. And so if you're looking in this direction, for example, you see normal stars, a screen of stars that you see. Actually, the center of our galaxy is not very well visible from most of India. If you're going to the south, you can probably see a little more of Sagittarius, which is this part. But this, for example, is a view from Chile, where I go a lot to use their telescopes. So some of the best telescopes in the world are in northern Chile, in the Andes mountains, in the Atacama Desert, dry place and high place. And so this is the 4-meter telescope in Cerro Tololo, and you can see how lovely the plane of the galaxy looks in the sky, the Milky Way. That's the center of the galaxy in there, and the black hole would be right there. These are 2 satellite galaxies of the Milky Way, which you can see from the southern hemisphere, called the Magellanic Clouds. They're naked eye objects. You can see them in the sky. They're like clouds that don't go away. But here you are. So I mean, in a place like this, when the Milky Way is up, you can read by starlight. You don't need the moon. So here you are. So the idea is that there is a big black hole sitting right in the middle. How do you see it? First of all, in the plane of the galaxy, there's a lot of dust. And this dust is essentially solid hydrogen, and a lot of the dust, kind of dust that you find in your house as well, silicon dioxide, that kind of stuff. And these are things that either didn't get into stars when stars were formed, or byproducts of stars as stars explode, and these are processed in stars. So a lot of stuff that lies in the Milky Way, in all galaxies, that is, around star-forming regions. And in the plane of the Milky Way, a lot of stars are being formed, and so there's a lot of stuff that's either pre-star formation or post-star formation, and they block light. So as you can see, I mean, this is a picture taken through light, and you can see if for example there's a black hole there, how would you see it, even if light came from it? So, but what I want to do here is we want to look at stars that are very close to the Milky Way and see and measure their motion to see how fast they're moving to find out what the mass of the black hole would be, right? even if I don't see the black hole. So for example, if you look at the solar system, and if you actually measure how fast the planets are moving, even if you didn't see the sun, you can measure the mass of the sun, right, from the Kepler's laws, yeah, just from the motion of the planets. So if you see the center of the galaxy, and if you measure the motion of the stars, you can measure whether there is something that is very massive, supermassive, that is causing that motion. So that is one way of finding the black hole. Now, to do that, first of all, you need to get through this dust, and that is why you need to observe in the infrared, not in optical. Infrared light is not absorbed by dust. Near infrared, I mean, you have to go at least above a micron or so in wavelength, which is beyond our eyes. But also you have to look very close to the black hole, and so you need to use telescopes that have very high precision. And so we are now making mirrors that by a process called adaptive optics, in which the mirrors, the shape of the mirrors can change, responding essentially to changes in the turbulence in the atmosphere. And what happens is that as light comes through the atmosphere, the light comes through the atmosphere, because the made up of layers that has its own pressure, temperature, and they light comes through the atmosphere and it's being refracted at every. And when it comes to us, actually, the image that it forms changes position many times. This is called stars. The whole feeling of stars, twinkle, twinkle, little, is that the comes to the atmosphere is moving around because of this variable refraction. A long exposure picture, star or galaxy or whatever, this is averaged over a large area, image gets blurred. This is why space telescopes are. So now, largest telescopes, which of course computers can sense by looking at some star that how this process is going and how fast this speckle, the image of a star, is moving, and it can send information mirror of a large telescope, which it can deform itself slightly to show point. This is a fantastic method called adaptive optics, which has been perfected in the last, say, 20, 30 years. And some of the largest telescopes that are being built can actually use this sensing of the atmosphere and how the wavefront coming through the atmosphere is distorted and compensates for it. And this has now been used to look at the galactic center, say here at 2 microns, for example, in the infrared, to find out, where these stars are near the central black hole, right? So this is a wonderful thing, and this is how we can get close to the black hole. So here we are. I can show you this whole thing, and if you can look at what's happening here, let me show you. Here is where the center of the black hole of the galaxy is, and we cannot see what's there, right? But what you can see are actual observations taken from 95 onwards till now. Here's the up-to-date picture here. This was published only last month. And from 95 onwards till now, you can see pictures of all these stars observed every night. And their orbits have been mapped up to now, right? And star SO2, it has a period of about 13 years or so, and it's gone around, and it's exactly like what happens with planets in the solar system. You can measure the mass of the sun using that. You can take all of these little stars near, and using this adaptive optics, you can see and measure their orbits, and voila, you get their masses. The 2 groups that have been doing this, the pictures that I showed you right now, comes from Andrea Gheze's group in UCLA using the Keck telescope in Hawaii, And then Reinhard Genzel's group in Munich have been using the VLT in Chile, and they've both done amazing work of doing these. And so there are lots of people, including our students, who actually study these orbits of these stars that are very close to the galactic center. And, this is, so sorry, it's 15 years, I said 13 S2's period, and you just can use Kepler's laws. Sagittarius A star is where the black hole should be, and just even long before, even 2002, one could fit what the mass of this black hole is, and the mass of the black hole is 3.5 million times the mass of the sun. So here you are, and there's nothing that can have that kind of mass and be confined within such a small volume such that these stars are not hitting them, right? You can have clusters of stars that would be 1 million solar masses, but they would be much, 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 much bigger. Their sizes would be much bigger. And so, so this is one way. Defying Hawking is one way of actually finding a black hole, observing a black hole, because you are measuring the direct dynamics as a result of the black hole. You also know, of course, last year the Event Horizon Telescope actually published an image of a black hole that's in a galaxy M87, which is about 15 megaparsecs away from us, and this is the central black hole, a few billion times the mass of the sun in the middle, and here essentially what you're seeing is light from close to the black hole, and you can see essentially that there is a black hole in the middle where light cannot come out. So this was another way of actually directly imaging the surrounding of a black hole rather than looking at the dynamical effects. And you've read all about it. I'm not going to talk much about it because it's very recent news, and there was a lot of stuff written about it. Come back to it later on. So here we are. We're talking about supermassive black holes, but then there are stellar mass black holes as well. And let me quickly talk about two other kinds. So we know that in general, you have light. We looked at the pictures made out of light. This is actually not a picture made out of light. This is an image made out of microwaves. This is a microwave emission from near the black hole. Here we looked at, these are all stars which are captured in the near infrared in 2 microns. But normally, so the near infrared would be around here. This is your electromagnetic waves. You're looking at wavelength in meters and frequency on the other axis. Our eye is sensitive to only this little part, which goes from after ultraviolet to less than infrared. In this wavelength is increasing this way. But in the electromagnetic spectrum, you have all this stuff. You have radio waves. You have X-rays and gamma rays and cosmic rays. X-rays and gamma rays are very tiny wavelength, nanometers and less, and so they're very high energy. The longer the wavelength, the energy becomes smaller and smaller because energy is related to frequency, right? So one of the things that happens is that when you have black holes, the area around it can get very, very hot due to the gravitational pull of the black hole, and so it will emit a lot of high energy photons. So you can look in X-rays, gamma rays, things like that. But what happens for our atmosphere is that our atmosphere does not let in most of this radiation. So you have this optical window. So you look at this, that's the optical part which our eyes are sensitive to. But and that's a coincidence. Think about it. And it is a coincidence that actually our atmosphere lets in that amount of light. This is the transparency. So you can see there's a window just around there where the atmosphere lets in light. And there's a radio window. That's it. And infrared up to, so this, the picture I showed you of those stars are around here. There are some windows here. But if you go to longer wavelengths, right, like in the radio microwave here, or in far infrared, or shorter wavelengths like in ultraviolet and X-rays, the atmosphere stops it, and which is very good for us, I mean, because of course, if we had an ultraviolet and X-rays come in through the atmosphere, then our skin would develop problems, and we won't, we'd have lots of disease. But the problem is that if you're looking at X-rays from around black holes, you need to go to space, and so you need essentially space-borne telescopes to observe these things from up there. And this is why this is a new subject, because we really did not have space-borne telescopes till a few decades ago, and so we that is why in the 80s Hawking was still saying how can you ever observe black holes. So I was involved in the construction of this particular observatory, which NASA flew in '99, and this was the job that I did at Harvard, where this observatory was built, named after Chandrasekhar, which is called Chandra, and its entire mission, was the primary mission was to look for black holes, in looking at effects of matter falling in to the black hole and getting heated up and emitting X-rays. It still is operating. It was supposed to be 5 years in operation in '99, and now it's 21 years old. And Chandra is a lovely instrument in which mirrors were built for the first time that would actually image X-rays, and so have produced these amazing images in X-rays, which are similar to the best optical telescopes like the Hubble Space Telescope. Before it and after it, such mirrors have never been built, and so Chandra is a very unique observatory, and the person who built those mirrors is actually passed away, so I don't know who's going to build it anymore. So Chandra is a wonderful observatory that actually has this very long orbit. The Earth has these radiation belts around it. Chandra goes far beyond it, goes all the way up to 122,000 kilometers, comes in, never comes closer than 26,000, right? And Chandra is actually shut off here, and it goes and comes in each orbit, 64-hour orbit, and is shut on. It's turned on around here, and it only observes during this period, because once it comes very close to the Earth, the radiation belts produces particles and high energy photons that swamp all the observation that comes from outside. Now, the interesting thing is X-rays. X-ray imaging is very difficult. Why did I talk about the capability of imaging X-rays? You need to observe very close to these black holes, but then imaging is very difficult in X-rays, because, as you know, X-rays go right through things. So if you want to build a mirror which is based on normal incidence, light falling on something, it's going to go through the mirror. But people realize that that you can. Why does it go through the mirror? Because mirrors are built of materials in which the interatomic spacing, or the particle spacing, is of the order of nanometers, and that is the wavelength of X-rays. So it's like throwing a ball, at a fence in which the spacing between the pillars or the rods is the same size as the ball, or larger than the ball, so it'll go through most of the time. But what you can do is, if you turn it around, if you turn such a wall around and try to throw it at a small angle, it's going to hit the wall much more, right? So this is why X-ray mirrors are built at grazing incidence, which means that the X-rays are incident at a very small angle, not more than 2 degrees from the surface, and as a result, it can be reflected. And these X-rays then can be reflected on, and so the mirrors are very long, they're cylindrical, as you can see. Chandra is about 4.5 meters long, and so these are then built as paraboloids, and I don't know whether I can show this to you. Yes, so what happens here, is that the X-rays come in and they are shepherded towards a focus through these nested mirrors that slightly reflect these at every incidence, reflect these photons, and then they are detected. There's not many of these there. For example, sat, which is in orbit right now, mirrors, but they produce images which have resolution of a few minutes of arc. Chandra has the resolution of half an arc seconds. That's the best mirrors ever built. So what are we trying to detect? Here is a scenario. So what you have is, you have stars that that would evolve, right? I told you that Chandrasekhar said that the stars evolve. More than half the stars in our galaxy are in binary systems. Stars don't like to live alone; they live in pairs. And if you have two stars, and our sun is an exception because because Jupiter almost became a star, it didn't. Our sun has, and that's why we have one sun in the sky. Most planets should have more than two or more suns in the sky. Now, if you have two stars, and one star, of course, would be bigger, and the more massive a star, the faster its evolution, and so it will evolve. So here you are. If you have two stars that are going around each other, and one star ends its life, it goes supernova, and say turns into a black hole. Okay, so the other star is now going to evolve a little slower. And as it evolves, towards the end of its life, it grows and becomes red, and is about to end its life. But as it grows, its outer surfaces become further from its center, and so here is a black hole that is very nearby, and it starts pulling the outer layers of this star. Right, this is a very common scenario in binary systems. And so this mass starts on to compact star. It could be a black hole, which has evolved, first, and this mass that comes from the companion star, as it falls on, this compact object gets very hot because the black hole's gravity is very, very, very strong, and what happens is that it turns into, it doesn't fall in straight in because it has a lot of angular momentum. It can't directly fall into a black hole, just like, the Earth is not falling into the sun, it's going around. So stuff that has angular momentum cannot destroy angular momentum that fast. And so it forms a disk around the black hole, right? And that disk gets very, very hot due to the gravity of the black hole. And it gets hot at 10 to the past 7 degrees or so. And they become, and 10 to the power 7 degrees, predominantly a plasma. Full of X-rays, right? So gas falling into a black hole gets very, very hot and emits a lot of X-rays. So here is a good example of an observation, Chandra. This is my own work because we worked with the Chandra telescope. Building it, we had a lot of guaranteed time that we could use. And so here's a good example of a nearby galaxy called Centaurus A, which is a nearby galaxy with two galaxies have collided. As you can see, this is an optical picture in which all the stars that you see belong to this galaxy, but these are normal stars. This is an optical picture. So this is a picture taken by a telescope on the Earth. Now, when you see stars in a picture like this, all of these things would be a few thousand degrees hot. The Planck law, the black body law just tells you that something's a few thousand degrees hot. It emits mostly in the optical. Its peak will be like our sun in the yellow, in the green. It's like that. But if you turn Chandra on the same scale to this particular galaxy, this is what it looks like. So this is a million seconds on Chandra, built up over a couple of years, and you can see what every single thing in this particular, on the same scale, right? Every single thing that you see in this particular picture is more than 10 to the power 7 degrees hot. Okay, so here you are. You can see that that's the center of the galaxy, and the center of the galaxy, there's a big blob there. Yeah, and all these are little things, and these are all X-ray binaries. These are all binaries where there's a compact object that is pulling mass into. That's the only way you can do it. to produce blobs like this in X-rays, which is very, very high energy. And the center is a very big black hole, which is actually pulling in a lot of gas. And what happens in central black holes in galaxies is that the gas falls in, but cannot fully fall in at the rate it cannot go into the black hole at the rate it falls in. So a lot of it is ejected in the form of a jet. It's like a black hole vomiting, eating too much and vomiting. And so here is this jet that is moving actually at 99% of the speed of light, and it's 10 to the power 7 degrees hot. This is why you shouldn't go near a black hole. So here you are. So and so here in this particular picture, you see a supermassive black hole and lots and lots and lots and lots of, actually not of all of these extraboundaries black holes. Some of them are neutron stars. I had a PhD student do his entire PhD thesis on each of these objects, and he found that there are at least 5 of these can be proved to be black holes by spectral analysis of the X-rays and looking at how they vary from time to time, etc. So here you are. So you can actually detect black holes, both the kinds of black holes, by making X-ray observations. Okay. So can somebody tell me how much time I have left? How long can I go?
It's 6 or another half an hour you can take.
Half an hour. Okay. No, I don't want half an hour. I'll be happy.
Yeah. You please carry forward as you feel free.
Okay, good. No. So I just thought I'd go into another way of course, this is very topical. Another way of looking at black holes. Yeah. So I should finish in another 10 minutes. Yeah. Otherwise, people get very hungry. Anyway, so you know what's happening now in India is that in India, I just came off a 3-hour meeting with the DST and the principal scientific advisor to the Prime Minister and things like that on a discussion on mega science projects, how what India's role should be on mega projects. And mega science project means that the Indian government spends more than $100 million on a particular project. And you know that these are in physics. India is involved in some of the biggest projects that are going on in the whole world. We are involved, I am involved in a big way in building this 30-meter telescope in Hawaii, just next to the Keck telescope that produced that fantastic picture of those stars going around the central black hole. There are 5 countries, India, China, Japan, and Canada and the US planning to build a 30-meter telescope. We have the Square Kilometer Array, which is going to be the biggest radio telescope in the world, and India's a partner there as well, along with 15 other countries. And it will be an array of radio telescopes all over Australia, Africa, etc. And all of these, we have now become an associate member of CERN, etc., etc. But one of the biggest things that we are going to build in India is called LIGO India. It's a gravitational wave observatory, the 3rd one in the world. And I'm very proud that IUCA, my institute, is one of the institutes that will be involved in building it. So I'm going to come to that in a minute. I just go through it. And so this is LIGO India. This is what it's going to look like. And this is our architect who's now planning the entire landscape, has come up with a very colorful map of what LIGO India will look like. This is going to be placed in a place called Hingoli, which is in Maharashtra, near the city of Nanded. And we've just finished buying this whole plot of land. This is 4 kilometers by 4 kilometers. And a lovely place. And the 4 institutes that are involved in building this is IUCA, which is this, and then the 3 DAE institutions, RRCAT Indore, IPR, Institute of Plasma Research in Gandhinagar, and DCACN as part of PRC in Bombay. And I think this is the best way of detecting black holes, because these are, as you know, direct measures of black holes. And what we're doing here is not measuring electromagnetic waves, but we are measuring gravitational waves. We are detecting and finding gravitational waves. And as you know, a couple of years ago, the Nobel Prize was given for it. The first detection happened almost exactly 5 years ago. And in the discovery paper, lots and lots of Indians were involved, both in India and abroad. And what happens here is, I told you that Einstein redefined gravity, and one of the predictions of Einstein's gravity was, of course, light bends because it goes through, distorted space-time. But another big prediction of Einstein's gravity was that as things move in space-time, it will send ripples in space-time. Because space-time is a thing. In Newton's gravity, space-time didn't exist. But now, if space-time is it's a fabric of space-time, it will just like when a duck moves through on a pond, it causes ripples and things will. But then Einstein wrote a paper in 1916 saying that you'll never detect these things because he calculated what the amplitude of these waves would be, and these waves would be so small that you'll never be able to detect it. And so Einstein said, don't bother looking for it, but here's a prediction, right? And so the idea is that gravitational waves actually cause space-time to move to vibrate in particular directions. And for those of you who are familiar with Michelson interferometer, an interferometer is a thing in which light, electromagnetic light, lasers coming in a particular direction split into two orthogonal perpendicular directions and brought together again. And because they come from the same light, they should be in balance. But what happens in a particular case like this, if space, as when gravitational wave goes, if space-time itself vibrates this way, then the vibrations along one direction and the one along the perpendicular direction would happen in different ways. And so they can be detected by an interferometer like this going out of balance. So here it is, the LIGO Laser Interferometer Gravitational Wave Observatory. There are two of these in the US, if they work like this. So here you are, light comes and being split into two parts, and these are 4 kilometers long, each arm, and they reflect off these mirrors and come and combine here and produce a static system of fringes. Now, a gravitational wave going this way, if it makes the space-time itself contract this way like this, but expand that way, then these things would go out of balance, and the fringes would be detected. That's the idea. The problem is that the expected deformation for kilometer arms is 10 to the power minus 18 meters. That is because the actual strain, the delta L over L is 10 to the power minus 21. And so for a detector that is kilometers long, which is the maximum you can make, because on the Earth, you can build a straight instrument only up to about 3 or 4 kilometers. Beyond that, the Earth's curvature prevents you from making a straight thing like this. So 10 to the minus 18 meters. Now, note that the size of the atomic nucleus is 10 to the minus 15 meters. So you're going much smaller than the atomic nucleus, and this is why Einstein said, of course, this is not possible, right? So you can see how LIGO's sensitivity is even smaller than the nuclear diameter. But this was done, right? And this was done 5 years ago. So this is the great thing of these two observatories in the US, which are 3,000 kilometers apart. Both detected the first gravitational wave in September 2015, and it looked like this. And so, and this whole thing, see, is only about 1/5 of a second. And in 1/5 of a second, what happened was two black holes that orbiting each other collapsed together to form one single black hole. And all this happened within this amount of time. And as a result, the ripples that went out from that event, which happened so far away, reached the Earth at the same time. It reached Hanford and Louisiana about 7 milliseconds apart. So because it came from a direction, it told us which direction the wave came from. And you can see that because two black holes going faster and faster and faster and merging together would actually have a signal in which the frequency will go up. It is here as the frequency is a function of time, it goes up like that. So, I mean, this is a separate topic of talks. I didn't want to go into the details of this, but I just want to tell you this is a good way of actually detecting black holes, because you're directly detecting not through any electromagnetic radiation that comes from near a black hole, like the examples I gave you, but what you're doing is you're detecting the black holes themselves and their effect on space-time. So this is one of my students actually produced this lovely graphic that I used in the article in Anandobajar I wrote the next day of the discovery. It's wonderful to show the Schwarzschild radius of the black holes that were discovered in that first event are the size of large states in India, right? So this is the Schwarzschild radius of the black holes that were found of about 30 solar mass black holes merging together to form something that's like, actually it was 29 and 46 solar mass black holes merging together to form a 62 solar mass black hole. And if you see the difference of the two, the numbers, you'll find that 3 solar masses are missing, and that those 3 solar masses are mc squared turned into 3 mc, 3 masses of the sun times c squared turned into energy, which is the gravitational waves. So Anirban produced this lovely picture just to show, that's what these sizes of these black holes are. Now, I remind you that I just told you we found this one was 60 solar masses, but that I just told you that normal black holes that we find from X-rays, etc., are a few times the mass of the sun. So here, from these LIGO measurements, we are actually finding these very massive black holes. Just to give you an example, I have of course the latest run of the LIGO was cut short because of the pandemic. But just last year, I just took the statistics of when the third run started in April 2019, each of those dates that were marked were a discovery, right? And before the third run of LIGO ended in March this year, by the time in the last 5 years, we had detected about 65 or so events. So these are happening now. Sorry, and I wanted to show the kinds of events that are being detected. Now, this is a very lovely image. It shows you. I don't know why it's not staying. It shows you in the LIGO event you have 2 black holes merging into another black hole, right? This gives you the mass of the black hole. So from the X-ray measurements of neutron stars or black holes, EM is electromagnetic black holes or electromagnetic neutron stars that we have measured from the X-ray measurements of Chandra-like things that I told you. These are the real events that have been measured. And you can see we've been measuring, we've been finding neutron stars that are 1 or 2 solar masses like Chandra predicted. We've been finding black holes that are 5, 6, 7, 8, 9, 10 times the mass of the sun, right? But LIGO has given us these amazing objects. And these are just some of them. I haven't shown you all of them yet. But the most massive black holes that we found out of LIGO are almost 80 times the mass of the sun, right? So this is getting to a stage where we can now challenge people who can say these intermediate mass solar black holes do not exist. In fact, there are some unpublished data that I know, because I'm part of this collaboration, that actually we have evidence of things that are more massive than these, which will be slowly published now. So so these are, in LIGO, we are detecting a different kind of black holes because we're directly detecting them. And of course, these are the ones that will cause the maximum commotion on the space-time as they merge, and we can detect them. So the future of this is this. We will have a LIGO in India hopefully from 2026, 27. And one of the great things that will happen by then is that we will have built up quite a lot of detections of these exotic objects. And LIGO India, being the other end of the world, is going to make a huge difference by it will help us pinpoint where these things are coming from. Right now, the problem with each LIGO is that it's like a microphone detecting a sound. It can't tell you where the gravitational wave came from. The 2 LIGOs in the US have a very limited way of pointing which way it came from. Right? By having 3, you can triangulate and say where it came from, and then you can turn all the other telescopes on such an event and trying to figure out what else happened when these two things merged. And so we can find a lot more about black hole physics that way. So right now we have these two LIGOs. There's a Virgo, which is already started observing in Italy, which is built by the Europeans. It's a 3-kilometer long observatory, and Japan has built something called Kagra, which is only very recently started working, but hasn't detected anything yet. And LIGO India will be now approved, but will be built there. If you want to know more about LIGO, go to social media. We have a very formidable Twitter and Facebook presence, and you can see a lot of stuff happening. And I'm going to stop here now and put up these list of books. If you want to read about black holes in general, there's some lovely books are out there, and I'll stop there and take questions. Let's see if I can stop the screen sharing.
Thank you, Professor Raychaudhuri. It's a wonderful, wonderful session. So everybody, you made everybody keep quiet.
Okay, I have time. Okay, go ahead. Yes, thank you.
Like every time, this time also we are mesmerized. So, now I think our scholars would like to raise some questions.
Yes, the session is open now. You are now free to ask questions, but one by one.
Is there a way of hand or whatever? I can't see. Somebody has to moderate. I can't see everywhere on everybody on my screen.
You can just minimize the presentation screen, then you can see everyone else.
Not everyone.
Not everyone.
Yes, you can. So,
but hand here, or somebody, or you can pick.
You can see us. So is there anybody going to ask question first?
I think Abhijit will moderate.
I see here a question from Shilpa. What is the nature of gravitational wave? Mechanical or electromagnetic? Is the question.
Go ahead.
Yeah.
Hello, sir.
Who is this?
Can you hear me?
Yes, I can hear you.
Shilpa Shamaddar.
Go ahead.
Actually, I have two questions. One is, you have told that black body is actually plasma. Is it so?
No,
because
I two different things, right? Plasma is something that all the charged particles are separated from each other, so you don't have things in atomic or molecular form, right? So you know these states of matter, you have solid, liquid, gas, and plasma. Plasma, all the charged particles are separate. So at a certain temperature, matter cannot exist in a structured form like in a solid or a liquid or a gas. And so it's a plasma. Now a plasma, because it has a certain temperature, will emit. And it can be a black body. Plasma can be a black body. And so, for example, the sun is a plasma. Sun is completely plasma because, in the middle, its temperature is 10 to the power 7 degrees. On its surface, its temperature is 10 to the power 3 degrees. And it is essentially in a plasma state. But the sun is also a black body because it's emitting in these different layers as a black body. So a plasma can be a black body, but two things are different. It can emit as a black body.
So sir, black body means plasma. From the plasma, visible range can be radiate, means but from the black body, which radiations are coming, that is not under the visible range, right? That is under.
Depends on what the temperature is. You know about Planck law, right? You know about the black body law. So a Planck law gives you the shape, a Planck curve of the shape is in the spectrum. It tells you the shape of the spectrum, and it tells you that it peaks at a certain point, which is given, as you know, by Wien's law, which you learned in school. So the peak of the black body determines where most of the radiation from the black body is emitted, right? So, for example, the sun is 6,000 degrees at its
Sir, voice is not coming.
There might be some. Yeah, now it's coming maybe.
Okay. Yeah. So the peak of the black body, that is the sun, is in the range of yellow or so, right? Of green, and this is why you see the sun in a way. If the sun was 12,000 degrees, then that peak of the black body is blue. If the sun was 3,000 degrees hot, then the peak of that black body would have been in the red. The sun would have been a red star. You see, Ardra, Betelgeuse, is a red star, and that is because its surface temperature is 3,000 degrees, right? A newborn star would be extremely blue, or even in the ultraviolet. You won't see most of its radiation. And if it becomes 10 to the power 6, 10 to the power 7 degrees, that plasma, then it emits mostly in the X-rays. It does not emit in the visible at all. So, for example, the sun's corona is 10 to the power 7 degrees. It emits X-rays, but it does not emit light. Do you see what I mean? So that is what I meant. Anybody else?
Yes, there are.
So I have a question. Am I audible?
Yes. Carry
Go
on,
ahead.
Shreyansh.
So my question is, when gravitational waves are occurring, that means there is a ripple going on in space and time. So how are we going to interpret that ripple in time through our theoretical basis?
Okay. Yeah. This I should have given a lecture only on this, not just black holes. But you're right. Space and time are not separately in general relativity. Okay. So in Newton's form of discussing physics that we learn in school, space and time are two different things. Yeah, you have space, you have time, you have x and y, and you have t.
Yes, sir.
Einstein showed us in his formulation that space and time are actually connected together. Space and time are actually reality. Space-time, that's why we call it space-time. Reality is actually four-dimensional. Time is just like space, but it's another dimension. Okay, so we don't call it space and time. You can't call it separately. You can't see it separately. So the Schwarzschild metric I talked about, I didn't go into the mathematical details. Einstein's theory writes space-time in terms of space-time, which is four-dimensional. Okay, it shows the curvature of space-time together. Yeah.
Okay.
And the Schwarzschild metric shows the shape of space-time together. Okay. So there is no curvature in time separately, curvature of space. And so I'll give you an example. It's a very interesting thing. What is the difference between space and time? In space, you can go in both directions, right? I can walk up and down in my room. I can walk up and down in this direction, X, Y, and Z, right?
Yeah.
In time, you cannot go in both directions, right? You can only go in one direction. So that is a fundamental difference in space-time. So even in this four-dimensional space-time I'm talking about, time is special. That is because in time, you can go in only one direction. In the other three dimensions, now, it is very interesting that if you look at Schwarzschild's solution of Einstein equation, it shows that inside a black hole, you can go back and forth in time, but you can go in only one direction in space. So space becomes time and time becomes space inside a black hole. And that is why nothing can come out of the black hole. You see what I mean? So this kind of shows in a very interesting and extreme way how space and time are actually interchangeable. It just every dimension has its own characteristics. So the picture I showed you of around the sun, space-time being curved, it is a four-dimensional thing, but we can only see three dimensions. We can't visualize four. And that was the space part of the space-time. So think about a four-dimensional manifold, four-dimensional thing, in which you're taking a projection on three-dimensional space, right? You can project a three-dimensional space or into a one-dimensional space. So,
Yes, sir.
and thus we saw a three-dimensional space. But actually, the thing is four-dimensional, and so that is why it is called space-time. And so then you can go into mathematics and solve Einstein's equations in 4 dimensions, and all these things come out of that, right? So
Okay,
I
sir.
think that is the straightforward answer to your question without giving you a 3-hour lecture on space-time.
Okay, sir. Thank you, sir.
We'll be happy to organize your that lecture as well. So
Thank you.
once the time permits from your end.
I
So
can
another question is,
separate talk on LIGO later on. Yes, go ahead.
yeah, sure.
Sir, I have a question.
Yes, go ahead.
Yeah, Zahid.
Sir, my question is in electromagnetic waves, energy is stored in electric field or magnetic field, but how gravitational waves carry energy, or how energy stored in the distribution of space-time?
Excellent question. I mean, all waves are a way of transporting energy, right? Yeah. So now you have a problem with this because we are only used to electromagnetic waves. We haven't, we didn't know about gravitational waves till recently. Everything that we see or perceive as electromagnetic wave, and it is caused from electromagnetic disturbances. So, for example, this light that I have here, this light is producing an electric field and a magnetic field, and there are variations in it. And as a result, the disturbances produce this electromagnetic wave light that comes to us, and that is illuminating my face. And that is because it has electromagnetic field in there. And so that energy is being transferred in the form of light through this here. I mean, it doesn't need a medium. As you know, electromagnetic waves can go in vacuum as well. So, but that is an effect of the forces of electricity and magnetism. But Einstein showed that because gravitational force is different from electromagnetic force, there too, in the gravitational field, if changes happen, then there is energy stored in the gravitational field in the form of potential energy, and that can be transferred through these waves, right? And so it is independent of the electromagnetic wave. That is why gravitational waves have this amazing possibility now. We have now a totally different astronomy that we can do. Imagine Galileo discovering his first telescope and seeing things through a telescope and detecting light from something. Now, we can only see through these telescopes things that have electromagnetic fields and their variation. What if there is something where there is no electromagnetic field, like a black hole? There, you can only see through its gravitational effect, right? So the universe is now opened up to a different kind of phenomena in which we are sensing variations in the gravitational field, not its electromagnetic field. They are related maybe, and that is what we want to know. What is the relation between the two? You saw in that case where two black holes merged, and 29 plus 46 became 62. So 3 solar masses worth of energy, of mass was transferred into energy, 3 mc squared, m star c squared, and m sun c squared. That was released in the form of gravitational waves. And that came to us, just like light comes to us, in the form of this gravitational wave. Do you understand this now? So this is energy being converted from mass into energy rather than electromagnetic field into energy. Okay. Right.
Okay, sir. Thank you, sir.
Question, sir. Sir, I'm Swati. I have a question.
Swati, yes.
So, gravitational wave is the ripple in space-time. So, does the wave change fundamentally in 4 dimensions as time changes?
All waves. Yes, of course. It's a strange question. I'm thinking about how to formulate your question. As I said, space and time are not separate, so you can't say it changes in time separately from changes in space. Okay, but a wave would evolve as it travels, right? But it travels through space and time, so it would fall off in its intensity and stuff like that as it travels through space-time. Now, I cannot separate out its effect in time from its its effect in space, if that's what you mean. So its evolution will happen as it travels through space-time, altogether. it doesn't evolve in a different way along time than along space.
Thank you,
Sir,
sir.
Sir, I have a
this
question,
is,
sir.
Sir, one question.
One by one, please.
Obviously, you have to moderate this.
Yes, yes.
Lots of questions for the chat box also.
hello.
And some people are asking questions in Latin as well.
Sir, actually, question.
Yes, Orchish, please carry on your question.
Sir, my question is it necessary for...
Other people mute? Yeah, Orchish only first.
Yeah.
Yeah.
So why does gravitational wave travel at the same speed as that of light?
Very good question. And, it's a prediction of Einstein's theory of relativity. Just like Maxwell's equations actually tell you that what the speed of the electromagnetic wave will be. If you've done Maxwell's equations, you know that it actually, if you write the wave equation, it tells you it's going to be c. Just like that, when you analyze Einstein's equations of gravity, it tells you that gravitational wave, the speed will be c. And that's very interesting, and that was a prediction from GR. It has been measured now, because there was one incident which about 2 years ago, 2017, which was a gravitational wave. I didn't talk about it. It came from the merger of two neutron stars. There have been 2 and 3 such objects that have been discovered now. One we've now discovered, which is a merger of a black hole and a neutron star, and 2 that are neutron star mergers. The one in 2017 was also a gamma ray burst, and we actually detected this event with electromagnetic waves as well, through radio telescopes and gamma ray telescopes and X-ray telescopes and all that. We found that the gamma rays that were detected from this event actually came exactly at the same time as the X-rays, and this thing happened. This thing happened almost, I forget now, some billion light years away, a few billion light years away. So you can see that in a few billion light years, the difference between the arrival time of the gamma ray and the gravitational wave was less than a few milliseconds. So it's essentially the same. Right? Yeah.
Thank you,
I
sir.
have a question.
Yes, Banik.
Sir, actually, my question was, we know that the quantization of electromagnetic field gives us photons, and also we have theoretically conceptualized gravitons. So has there been any experimental evidence of gravitons? This is my question.
Very good question. I get this question all the time, but very, very good question. Actually, nobody's been able to quantize gravity yet. And so conceptually, we can think of gravity being quantized, but nobody knows what a graviton would look like. Quantum gravity is still not a subject. It is a good subject to work on, but Einstein thought he would be able to do it in his lifetime, and he couldn't. So we don't have a mathematical picture of a graviton yet. But when that happens, then we would know what to look for. But currently, the detection of the waves that come, they're detected as waves. They are not detected as particles, the gravitons. But somebody is just waiting for a prescription of what a graviton would look like. In principle, they should be there, but we don't know what they look like.
Okay, so I have just one more question. Thanks a lot, and it was an amazing session. My next question would be, can we actually say about the existence of black holes through a sort of thermodynamic profiling? Through thermodynamic profiling, is it possible to say about the existence of black holes or where it should be found?
I don't know exactly, but I have read quite a lot of things, because there is a whole formulation of black, which was essentially started by Hawking himself, because he had an information theoretic approach of entropy, essentially, of the states of matter, states of energy that we hold. There are quite a lot of people who work on it. You of course know, I'm sure, Soumitra Sengupta, if he had talked about it, he would have talked about it. His group works on it quite a bit. Shumanto, who was a student here with Padmanabhan in Ayuka. Shumanto, who's in ICS now, does a lot of work on this. So this is a totally different form of finding what black holes would look like in multidimensional space. It also actually is a very good way of connecting to string theory and things like that. I don't think I'm going to go into all that now because it's a different formulation of black holes. It is one way where people think that if you want to have a quantum gravity, a quantum theory of gravity, it is a one way of bringing together the way we have a formulation of gravity and way we have a formulation of quantum mechanics, which also has, as you know, a very good connection with thermodynamics and entropy. And so that is a kind of formulation of it. But it hasn't given us a way of connecting the two yet. But please do go and read. I mean, I'll be very happy to talk to you separately on this kind of thing, or give you references and stuff like that. You have access to some great experts in Kolkata who work on this.
Thanks a lot.
I have a question, sir. Sir, can I ask?
Yes, Ashish.
Yes, Ashish, yeah.
Thank you, sir. Sir, I have a very simple question for a student up to class 10. How can I describe what is black hole in a simple way? If they asked question, because black hole, the word is know everyone up to class 10. If they asked in class, then how I can describe the what is black hole?
So that is why I introduced my talk in that way, right? If you take just my first 4 or 5 slides, where I start from Newton's theory, I talk about escape velocity from a star or from the Earth or whatever. That is something that is taught in class 9. And then you say that then there is a limit to the amount of velocity or speed that you can have, and that is the speed of light.
Yes.
And so a black hole is something from which even light cannot escape, so nothing can escape, right? So that is class 10 physics. And from that, you can go on to talk about what the size of a black hole would be because of the escape velocity argument, right? Even without going into Einstein's formulation. Right, so that is the way. I mean, I've given a talk like this to class 9, class 10 students very easily. In fact, recently I gave a talk at a planetarium in Delhi just before the lockdown. And I went there and found almost the entire audience was class 6. And it was no problem. I just talked to them about black holes. I had some of the best questions I've ever had from class 6 students. So, I mean, this is something that can be actually explained in these terms to even students in class 6 and 7, not a problem. Right. Yes, go ahead. Somebody else.
Yeah.
Can the Doppler's effect take place during gravitational waves?
Sorry, who? Who is this?
Sir, this is me.
Ashish.
Okay.
Hello.
Hello, go ahead. Yes.
Sir, my question is, does the Doppler's effect ever take place when gravitational waves are propagating?
Yeah, of course. Anything that where the source moves would have a Doppler effect, right? Doppler effect comes from the source, not from the wave itself. The wave carries the information of the movement of the source. So if a source moves, like a galaxy is moving away from you, the light that comes from the galaxy is the wavelength is shifted towards the red, and so you have a red shift. If a source that is emitting gravitational waves is moving, you have a gravitational redshift. So the frequency will change, or the wavelength will change.
So,
and you can measure.
So do we understand, I mean, do we know what a gravitational redshift or a gravitational blue shift looks like or something?
Yeah, but then you have to have measure the frequency of the gravitational wave and have a spectrum of the gravitational wave. So you have to measure it at different frequencies. So imagine you're doing this in 1900 or something like that for light. Newton has shown you that there's a prism and light goes through and you have a spectrum. But then you want to measure the change in frequency due to a Doppler shift. You can only do it for things that are moving very fast because your resolution is very small and you can see things going red or blue, becoming red or blue because of its motion. You come to the 1860s, 1870s, you have very sophisticated spectrographs and gratings and things like that. You can see lines, emission absorption lines, and then you can measure the shift of the lines rather than measure the whole thing moving, right? And now we have such high resolution gratings that we can measure even tiny motions of planets around other stars, less than a meter per second, whereas 100 years ago we could measure motion thousands of meters per second or kilometers per second. So in gravitational wave, the technology is like that. We can measure the amount of gravitational wave coming at certain frequencies only very in a limited fashion. We are very happy that we are detecting these things, right? Just wait for a few years and we will have a technology where we can measure the intensity of these waves as frequency, and only then we will be able to actually measure these shifts with frequency, right?
Thank you, sir.
Can I ask you a question, sir?
Sir, I have a
Wait a minute,
Sir, I have a
Ahon,
question.
Shurajit. I'll take your question. Anand was there.
Yes. Hello, sir. I'm Surajit Das. Sir, I have a question that from electromagnetic theory, we found that electric field and magnetic field are two type of dynamical variable, and we found that we derived some second degree equation of motion in time in Fourier space. So is there anything in gravitational wave or gravitational field which is called as a dynamical variable?
Yes, of course, and that's how you get a wave. Otherwise, how will you get a wave that propagates? The propagation and the velocity will have to come from a dynamical part, and that dynamical part comes from the gravitational field. There's a big difference between the gravitational field and the electromagnetic field. Because you're a student of physics, I don't want to get into that kind of detail because we'll leave other people behind, but you can read this. The gravitational field has a difference from the electromagnetic field in that you know that the gravitational field doesn't have a dipole component, because there is no gravitational, in electromagnetism, there is a monopole, right? You have a charge, whereas in a gravitational field, the lowest kind of harmonic is a quadrupole. So this is why you saw the way the space-time oscillates is like this, right? It goes in, expands in one direction and contracts in the other. That's the quadrupolar deformation. And you have higher order things as well. So energy is transferred from an initial disturbance in terms of these, and they all come from writing down the equations of motion in space-time, due to a gravitational field. So just like you do in Maxwell's equations, you put the electromagnetic part and magnetic part together, and then you write down an equation of motion. And for waves, it's the dynamic part that gives rise to the wave that carries the energy. Otherwise, it won't carry it through space-time. Through whatever, through the propagation. In the gravitational scenario from Einstein's equations, we have to write a dynamical equation. Remember, this energy is being transferred through space-time, and space-time itself is described by the Einstein's equation, right? It's slightly more complicated, but this is exactly the same way it is done. It's just the equations are slightly different.
Yes.
Sir, I have okay, sir. Thank you so much.
Ahon Boshu, you are having a question. Yeah, carry on.
Sir, in your lecture, you told that in the center of the galaxy there exists black hole. May I know why the black hole exists in the center of the galaxies?
So I said that, good question. I said that we see them, really. Now the question is, where else would it exist? First of all, we don't know where those things came from. I mentioned this, and we don't know because these things are millions or billions times the mass of the sun, and so there is no mechanism to produce them from stars. Probably the best way to produce them is that many stars which turn into black holes then merge together to form these monsters, right? So you can see in the LIGO detection, you can see a 30 solar mass and a 30 solar mass black hole coalescing to form a 60 solar mass black hole or an 80 solar mass black hole. So you already see this happening. Now you can imagine that over the age of the universe in a galaxy, such things can happen many times over. So this 80 solar mass black hole that has been produced will merge with another 80 solar mass black hole to create a 150 solar mass black hole, and so on and so forth. Eventually, it will maybe reach the million or billion times the mass of the sun. So that is one way of producing this. We don't know yet how this is done. But where do you think such things can happen? Where is the highest probability of such things can happen? Where the density of stars is the maximum. And that is where? In the center of a galaxy. Galaxies have a profile of mass distribution, whereas the maximum is in the center and falls off very rapidly, right? It also means that the gravitational field is at its minimum in the center of the galaxy. And so all the matter that is has a way of falling towards the center of the galaxy. So that is where black holes will meet other black holes, the maximum probability, with maximum probability. Matter will fall into black holes, thus increasing their mass with maximum probability. So eventually, this is probably telling us that if such things are formed from the merger of smaller black holes, that's where you find them.
Okay, thank you, sir. Thank you.
Sir, I have a question.
Sir, I have a question.
Okay, go ahead. Obiji, you have to control people. You have to assign a question.
Hello, sir.
Yes, go ahead. Who are you?
Sir, my name is Konat Shen, sir, and I have a question. That is, can we possibly tell is energy conservation valid at the center of a black hole or not? Means because nothing can escape from a black hole, so we have no information to tell whether the energy conservation is valid at the center of a black hole or not.
There is no reason to believe that it is violated because it's a fundamental physics and there is no way to violate it. Of course, you can measure theoretically, you can see what the effect of pumping energy into a black hole would be. The black hole's energy would increase. As a result, its mass would increase because mass and energy are the same thing. And so its radius would increase, right? Because its radius is related to its mass. So in principle, if you can dump some energy into a black hole, its size would increase and things like that. So there have been measurements to actually show how the size of the black hole is related to its mass. You saw the first picture that came out of the Schwarzschild radius of a black hole. Actually, it's not Schwarzschild radius; it's related to the Schwarzschild radius, but you can size the black hole essentially. So there are ways of measuring how the energetics of a black hole is related to its mass, and such things actually work out quite well. So there is no reason to believe that there is any special physics going on in the center of a black hole. True, you can't actually take a ohm meter and measure the resistance of a black hole by taking two wires there. Similarly, you can't really measure how much energy a black hole has just changed by dumping some energy in it. But there are astrophysical phenomena in which you can relate things, the two, and we can relate the energetics of a black hole to its mass content and things like that.
Thank you, sir.
Suppose, sir, I have a question.
Yes, go ahead.
Suppose I am very near to a black hole, and like a star, as the trajectory was given in your slide, that it is very, its velocity is very big with respect to our spatial coordinates. So can we describe the black hole invariantly with respect to any other coordinate? That is, I am saying that a length contraction will happen if I see the black hole in very big velocity. So will there some description problems in that?
Yeah, I mean, this is how, otherwise, how would you do it? I mean, if you are doing black hole physics, obviously you're a student of physics, so you can go and look at, let me refer to you to some very good books. I mean, if you look at, let me see, some really good books on gravitation. I mean, I showed you at the end of the talk also. Take a basic book like, for example, Jan Narlikar's book on gravitation, or Padmanabhan's book on gravitation, both of them. You will see that if you are looking at a particle falling into a black hole, you have very special coordinates that you use to actually deal with the mathematics. The original description that people used were, say, Finkelstein variables, for example, by Daniel Finkelstein. There are Stecker variables.
Yeah.
That also the effect of spin, as well as the falling into the black hole and stuff like that. There are various. Otherwise, it is very difficult to follow the trajectories of objects falling into the black hole. Every single, it depends on the formulation that you want. If you are looking more interested in the angular momentum and the black hole is spinning, then which is what these things are, and this is the kind of stuff that Kip Thorne had to do to do those fantastic simulations that he did for the movie Interstellar, for example, and as a result came up with a new formulation for doing these things, these trajectories. Though, and so things like that. So there are quite a lot of these formulations. So you are absolutely right. You need to work in very special coordinates.
Yeah.
And there are quite a lot of them. In fact, if you come up with you become instantly famous if you come up with a better coordinate than the others use it, and your name is attached to it. And this is why, for example, so famous. So just pick up a very good basic book on gravity. Bernard Schutz's book on gravity that came out a couple of years ago actually has a wonderful various different kinds of variables that are used in basic GR.
Okay. Thank you, sir.
Hello, sir. Hello, sir.
Yes.
Can you hear me?
Yes, I can hear you.
Sir, I'm
What's your name?
Ashmita. Sir, I'm Ashmita.
Ashmita. Okay.
Sir, we know that what is beyond a black hole? I mean, we know that any planet, it has a center, like Earth has a center, and it has a gravitational field. And when we move from the surface of the Earth towards the center, and when we actually go to the center, then there is no gravitational field. I mean, it's proportional till we go to the surface, and above the surface it is indirectly proportional. So in case of a black hole, where is the center? I mean, if we reach the center, is like there will be no gravitational or any kind of attraction towards the center of a black hole, or at the center?
You will ask me the hardest question possible. No, I mean, the answer to your question is we don't know. Of course, a black hole, because beyond the Schwarzschild radius inside, we don't have the physics to describe what's inside a black hole yet. We call it an event horizon, the surface of the black hole, for that reason, because whatever we see is outside the black hole. Once it goes in, we don't know. We only know that its mass is preserved, but we don't know what form that matter takes, and things like that. Of course, the black hole has a center of symmetry, right? So we are thinking of a black hole as some in kind of spherical coordinates, and then it has an origin. And so using this kind of the formulation that we have of gravity, we can talk about what the nature of space-time is as a function of r from that center of origin. But once you go inside the event horizon, we have absolutely no way of knowing. If we did, then we wouldn't have been able to, I mean, you know that we are foxed by the idea that at the center of a black hole, there has to be a singularity. There has to be things would go, infinite, like density and stuff like that. If you extrapolate from the description we have outside the surface of a black hole. And so the reason is that we don't know what's inside the black hole and what kind of form matter takes inside a black hole, and that is why we have no description of this singularity. So I think this is what you're talking about is a very open problem, and what you're asking is For example, if you go inside the Earth and right to the center of the Earth, you know exactly what the gravitational field would be, right? Because you know that when you're going in kind of spheres and go to the center of a spherical mass distribution, then you can calculate what's inside, and then you can calculate the gravitational field and stuff like that. For a black hole, you can't do that. You can't do that because you don't know what the distribution of matter and the distribution of gravitational potential is inside a black hole. You can only talk about the gravitational potential and measure it outside the event horizon. So it is an unsolved problem, but it's a very, very interesting problem. And I think, I mean, it has defeated people like Einstein and Stephen Hawking. So, I mean, maybe you are next. Somebody from here will do it.
Hello, sir.
So much, sir.
Yes, go ahead.
Hello, sir. Sir, I just have a question. Is it true that gravitational waves like around the surface of the black holes or something like that can bend light? Because light is also made up of photons. So is it true that it can bend light? And if it can,
I have a student here who's working on gravitational lensing of gravitational waves. So actually gravitational waves can bend too. Light, so all of this can happen. First of all, light is bent in space-time coming to you because the space-time itself is bent due to the gravitational field of objects, right? This is called gravitational lensing. So as a result, when you look at the images of stars, this is another lecture I can give you, but I won't, which is if you look at distant objects, you can see that light coming from them, coming through bent space-time, can come to you from different routes, and so you can see them, multiple images of them, and things like that. So you see effect of light bent as it comes along space-time. Okay. Now, similarly, gravitational waves can also be bent because they're coming through space-time. Now, as light encounters a gravitational wave, the space-time itself is vibrating, and so light will go along with this vibrating space-time, and so light will be bent additionally, right? The gravitational wave will add an extra dimension to it, an extra effect to it. So yes, as you absolutely right, what photon's job is to follow space-time and find the best way of getting to you. And if it encounters a gravitational wave, it will go up and down the gravitational wave and come to you. So it will interact.
Thank you, sir.
Sir, myself Harishankar Tripathi, and my question is, our current known physics is unable to predict what is happening inside a black hole. Is it true?
No, it can't. That's what I just said. I just gave that answer to somebody else, and I said that we don't understand what's happening inside the black hole with the state of physics we have now. No.
Sir, I had just one more question. Can I say to it right now?
Yes, go ahead.
Yes, sir. So as you have been talking about the coordinates, so we know that at the event horizon, if we work in Schwarzschild coordinates, then we have a singularity. But if we move to other coordinate systems, then we can remove that singularity at event horizon. So actually, event horizon is kind of special because beyond event horizon, we can't see anything. So does that singularity at the event horizon while working in Schwarzschild coordinates give us some sort of intuition that it is special in some manner?
No, all you're doing in this coordinate transformation is you are removing that singularity by making it insignificant, right? Because you're giving more prominence to where the information is. So it is a clever way of saying that I'm not going to consider anything beyond the event horizon. And so you make event horizon essentially zero, right? And you essentially work, and so there is no discontinuity there. It's just a mathematical trick. It gives you no intuition about what's beyond the event horizon. It's a mathematical trick to use normal mathematics in a coordinate system such that the singularity that happens does not introduce infinities and things don't blow up and stuff like that. So most of these variables that do these Finkelstein variables, Penrose variables, whatever, they all have to have this specific trick such that when you are, for example, taking the derivative of something, you can't take the derivative of something that is discontinuous, right? And so you make the coordinate system such that you can have normal mathematical operations operate on quantities, right? Written in terms of these coordinate systems, such that your normal mathematics, like taking a differential, taking an integral, taking whatever, such things work. So that this absolutely doesn't give you any insight. Otherwise, we would have got a lot of insight from the early work on GI. Have that. We don't know yet what happens inside.
Thanks a lot.
Okay, people have. Are there any other important questions?
I
Yes.
have a question.
Go ahead. See, we have lots of echo.
Excuse me, sir. Am I audible?
Yes, go ahead.
I have a question about the curvature of space-time. Sometimes we know that curvature of space-time is the gravity, and sometimes we also say that a massive body defines this curvature of space-time. Then what is the relation between gravity and the path defined by the mass?
I couldn't hear most of your question. Can you repeat that? Because there's an echo that I cannot really hear what you're saying.
Okay. There is curvature of space-time, and it is defined as the path defined by mass body. However,
Yes.
another time it is called as gravity.
Yes.
Then what is the gravity and what is the connection between gravity and the path defined by the massive body?
Right, very interesting question. I mean, actually, this is called the equivalence principle, essentially. So this is where Einstein starts from. So I would like you to read a very basic book on gravity, if you can, even if it's a popular book. It just shows you that these two are equivalent. That's the principle of equivalence, which says that the path taken, if you take Newton's laws and think about acceleration under gravity. And say a freely falling body in space, and you can just think about it as the motion along space-time that has been created, the curvature of space-time that has been created by the effect of that body in it, right? And these two are equivalent. So once Einstein expressed the equivalence between these two, only then could he move forward and say, look, actually, my description of gravitation does not say Newton is wrong, but it says that the underlying expression is the same in both. But in Newton's case, you cannot extend that theory into places where, for example, you can describe light, which Newton thinks has, photons have no mass, and so you cannot describe the trajectory of light in a gravitating field. Whereas Einstein just transferred that kind of the Newtonian description into this description. So these two are equivalent. And then once you have this formalism in which you think of gravity as just an effect of the curvature of space-time, and everything that moves along that curved space-time actually follows a trajectory that will be an orbit in Newtonian dynamics, then you have a formalism of dealing with high speeds and also and light itself, right? So it is just an extension of Newton's description. They are equivalent. They're the same thing. I don't know whether that makes sense to you, but I think you might have to read a basic book on gravitation to understand this.
Okay.
Sir, am I audible? Jyotirmoy Das.
Yes. Go ahead.
Hello.
Yes, go ahead.
Sir, we know that they are in the center of the gravity. Center of the galaxy. So, can we predict the mass of the black hole by predicting the mass distribution of the galaxy? Like, if the mass distribution of the galaxy like that, then the mass of the black hole will be like this order of something.
Very good question. Very, very good question. Yes, there is a relation between the mass of the galaxy and its black hole. Actually, very interestingly, I showed you a picture of what our galaxy looks like, right? In spiral galaxies, there are two kinds of galaxies, basically. There are elliptical galaxies, and which are ellipsoidal. And there are spiral galaxies, which are flat, disk-like galaxies with the ellipsoid in the middle. right? So it turns out that the mass of the black hole in the middle is directly proportional with some scatter to the ellipsoidal part of the galaxy. So for example, the spiral galaxy, in the center, there's a bulge-like thing, and then there's a disk. And it is the bulge mass that correlates with the mass of the, and in the elliptical galaxy, the whole thing is an ellipsoid. There's no disk. So that is why for the same mass galaxy, the black holes in the elliptical galaxies are much, much more massive. That is why M87, which is one you saw the picture of, has 10 to the power 9 times the mass of the sun. That's an elliptical galaxy. Whereas the one that is in our galaxy, even though our galaxy's mass is the same as M87 almost, not quite, but same, its black hole's mass is only 10 to the power 6 times the mass of the sun. And that is because it is proportional to the little bulge, the ellipsoidal part of our galaxy. So you're right, the ellipsoidal part of the galaxy, its mass correlates very well with the mass of the central black hole. And that is telling us something about how these black holes are formed. And there are lots of papers being written on this, but this is a very active area of research right now.
Thank you, sir. So I think it's already, we are about to conclude the session now.
Okay.
I think.
One last question from Shumona.
Right. Okay, Shumona. There are lots and lots of questions in the chat box, but I'm running out of time. So, okay, Shumona, go ahead.
Sir, is there anything called white hole, or it's totally hypothetical?
Question is going to come. I haven't never a question on black holes with somebody asking me about white holes. Thank you. Well, I don't know what that means, because I think these are theoretical that came out of some of the early things that Stephen Hawking wrote and stuff like that. People felt that if there are black holes, which means that there is nothing can come out of it, there should be an opposite to that, which is a white hole, which means, you know, everything comes out but nothing goes in, or something like that. I know of no such actual physical entity that would be like that, but there are things called wormholes, which are essentially networks that connect black holes, right? And think of, you know, going from one part in space-time to another part in space-time, and making a jump and traveling in time and things like that. And this is mostly a science fiction concept. And so white holes and wormholes and black holes, they are in principle, theoretically, you can you know, construct something and change the sign and stuff like that and say that this might be something, and give this is what Hawking did. So Hawking in principle created a kind of and called it a white hole, or you know, had these things connecting black holes. If as an observer you ask me how would you observe something like that, I don't know. I know how to observe black holes, but I don't know how you can actually take something like a white hole and detect them. So I would say that it's still a very much a fictional concept or a theoretical concept, and we haven't found any of them yet.
Thank you. I'm sure that everybody is very much excited, and there are a lot of questions coming on, and I would request Professor Rai Choudhury to allow us to give your email ID on the chat box. If someone is interested, then they can directly write to you, and with a reference of this seminar, and as and when you get time, you can reply them back, if you allow us.
Of course.
Yeah.
Yes, I'm putting my Gmail ID there, and okay. Chat box, please write to me. Okay.
It's like shomok.ayuka@gmail.com.
Yes, I just wrote it down. Okay.
Yeah. Thank you. Thank you very much. And,
thank you, Professor Choudhury. Thank you very much. And I think the scholars are really fortunate that they could interact in such a vibrant way with this renowned professor. But we will keep in touch with you so that you can give us next 2 days for, I think, one for space and time discussion and another for legal. So whenever you get time, please give us today's.
Two more lectures
to talk to
Steve. Yeah.
Okay.
Thank you.
Thank
so I request
Many thanks.
Bhattacharya to conclude the session now.
Yes.
Thank you.
All the scholars, I think you have enjoyed the lecture fully, and I saw that you have extracted as much as possible from Professor Raichaudhuri. So I think, and so you see that a senior JBNSTS scholar can contribute so much things to science. And I feel that this will be a great inspiration for you, that in your future times, you will also be like him to contribute the global scientific community. Thank you very much.
Bye for now. Thanks, everybody.
Stay well, everybody. Thank you very much.
Okay.